Hello everyone and welcome to the Vibration Lab. This is a bifilar suspension system which is capable to measure the radius of gyration of a point body and a line body. Before I start, let's try to answer how many degree of freedoms the system will have. If I will observe the system carefully, I can see here that this is a solid bar suspended with respect to these two strings. So if I am giving a gentle push in this direction, the system is going to oscillate. Similarly, if I will give movement in this direction, the system is going to vibrate. Therefore, I can say that these are the two degrees of freedom my system will have. If I will try to move the system in upward and the downward direction, I believe it is not going to vibrate because the strings are inextensible. Do you think the system will have any other degree of freedom? Yes, if I am going to give a rotation to the bar is going to vibrate or the oscillate about this axis of rotation. So this is my another degree of freedom. So I can conclude that the system will have 3 degree of freedom, but the last degree of freedom which I have shown is the actually we are going to use to measure the radius of gyration, and if we know the mass of the body, we will be able to get the moment of inertia. If I will see the mathematical model of my bifilar suspension system, I will see that a bar is suspended with the two strings which are 2a distance apart. The length of the string is L, and if I will apply the Newton's law or the D'Alembert principle, I will get the equation of motion of my system. Using this equation of motion, I will be able to get the time period or the natural frequency, and that is the formula I am going to apply to get the radius of gyration. So this is my formula, and when you will see here, you know L value, you know the G value, you also know the distance A between the two strings. Only unknown value is your K. So if somehow I will measure the time period of my system, I will be able to get the radius of gyration. So let's start our experiment and try to find the radius of gyration and the moment of inertia of this connecting rod. I am also going to find the moment of inertia of this circular peg, provided the mass of these two systems are available, because our experiment is going to give us the radius of gyration. So this is my parent system. My first job is to find the radius of gyration of this bar, and for that I am going to give a gentle rotation and I will measure the time period of my oscillation. Please remember, if you are not able to measure one cycle, you can measure 5 cycles or 10 cycles, and then you can average out to find the time period. Once you will get the time period of this bar, you can apply the formula where the A value, L value are given to you, and then you can get the radius of gyration of this bar. And as the mass of this bar is 1.6 kilogram, the moment of inertia will be just mk square. After getting the K and the MI of this bar, I can use another system to find the moment of inertia. I know the mass of this body. What I will do, I am going to superpose this body on my parent system, and again I will repeat the procedure. Here you must remember that the axis of rotation of the parent system, which you have already calculated, and the axis of rotation when you have put another auxiliary system should not change. That means the center of mass of the unknown system should be coincided with the center of mass of your parent body, and for that it should be known a prior. This is the limitation of bifilar suspension. I'm again going to give a gentle rotation. I will find the new time period, and using that I will get the new K value. So what would be the next job? I can subtract the previous moment of inertia from the new moment of inertia, so that I will get the value of MI of my unknown system. The last part of the experiment is to find the K value of this connecting rod. And what should be known a prior? The center of mass of this connecting rod. Assume the center of mass of the connecting rod is here, and the mass of the connecting rod is 374 gram. What I am going to do now, I am going to coincide the two center of mass, and again I am going to give a gentle rotation. I will measure time period, that is going to give me new moment of inertia. I am going to repeat the same procedure. I am going to subtract the moment of inertia of my parent system from the new moment of inertia. That is going to give me the K value and the MI value of my connecting rod. So I hope this demonstration helped you to understand how you can get the radius of gyration using bifilar suspension system. Let's summarize what is the limitation of your system and what are the important points. The limitation of the system is that if you want to find the moment of inertia of an unknown system, you should know the center of mass of your system prior. Then only you will be able to coincide the two axes of rotation and your answer will be correct. For example, I want to find the moment of inertia of a two-point mass system. If I am going to place the system asymmetrically with respect to the center of mass of my base system, then during the oscillation, the center of mass of the combined system, or I would say the axis of rotation of the combined system, will not match with the previous case, and then you will not be able to compare the two moment of inertia and it will not serve the purpose. That means this is the limitation of bifilar suspension system. About the degree of freedom, the system is having 3 degrees of freedom. One, this one, another one is the this one, and the third one is the rotational one. That is actually we have used to find the radius of gyration. Thank you.